Hello. So for section 3.4, we're still looking at applications of the derivative, and we're going to be looking at functions and their graphs and sketching their graphs from a calculus perspective. So these are functions that like polynomial functions that you guys have sketched in the past, like in pre-calculus and algebra 2, and now we're going to be using the derivative to help us determine characteristics about the graph so that we can do a rough sketch of them. So in pre-calculus, you guys determine the intervals where a function was increasing or decreasing just by eyeballing the graph, by looking at the graph and looking for where it looked like as x was increasing, y was also increasing, or whereas x was increasing, y was decreasing. And that's how you determined the intervals for where the function was increasing or decreasing. And here's that definition that you would have used. So if a function f is defined on an open interval, it's said to be increasing. That function f is said to be increasing on the open interval, we'll say from a to b, if for every x value on that interval, as x increases on that interval, the y values also increase. And then f is said to be decreasing on that open interval from a to b if as x increases, the y values are decreasing. And this is just the written definition that we used. So now we're going to be looking at using derivatives to help us determine where a function is increasing or decreasing. And remember, we've used a derivative to help us find the slope of a tangent line to a point on a curve. And we did this lots last semester and on your final exam. So basically, if on an open interval, the slope of the tangent line to every point on that interval is positive, then we can say that the function is going to be increasing on that open interval from a to b. So if we want to picture that, we obviously can't draw every single tangent line to the point of this curve, to every single point on this curve from a to b, but we could see that any tangent line we attempt to sketch would have a positive slope. Okay, so positive sloping tangent lines corresponds to the function increasing on that open interval. And then kind of the same thought process, but if f prime of x is negative for all x on the open interval from a to b, meaning that on the open interval, every tangent line has a negative slope, then we can say that the function is decreasing on that open interval. So we're going to look at this function. This is a polynomial function, a cubic. You guys have sketched polynomials like this before. But in part A, we're going to find all of the x values that correspond to horizontal tangent lines. So to do this, we're going to find the derivative of the function f and then set it equal to 0. Remember, because horizontal lines have a slope of 0. So f prime of x we can find just using power rule. And then down here, I will set the derivative equal to 0. And to solve for x, I'm going to factor out a -3 and then factor the difference of two squares. Okay, so now we're going to use those values of x to find the open intervals where the function is increasing in the open intervals where the function is decreasing. And the reason we wanted to find the location of the horizontal tangent lines is because to the left, if a function is going to change from increasing to decreasing, that especially a smooth continuous function like a polynomial function, that change is going to occur wherever there's a horizontal tangent line. So part B, I'm going to make an analysis line. I'm going to put the x values that we just found on that analysis line. And then I'm going to pick a number to the left and right of each of those values. So -2, 0, and 2. So I want to know what the sign of the derivative is to the left and the right of each of those values. So that's going to tell me the sign of the slopes of the tangent lines to the left of -1, to the right of -1, or between -1 and 1, and then to the right of 2. So I'm going to evaluate f prime at -2, right? That'll be the slope of the tangent line at x equals to -2. I'll evaluate f prime at 0 and evaluate f prime at +2. So when I do that, let's see. So for -2, there'll be -12 plus 3, so -9. So it'll be negative. The slopes of the tangent lines, I'll use blue, will be negative to the left of -1. And then f prime of 0 is +3. So the slopes of the tangent lines will be positive between -1 and 1. And f prime of +2 will also be -9. So the slopes of the tangent lines to the right of +1 will be negative. So the function is going to go from decreasing to increasing to decreasing. So we can say yes, this is still part B. Move it over here. The function will be increasing on the open interval from -1 to 1, and will be decreasing from -infinity to -1, and then also on the interval from 1 to +infinity. I'm just going to put a comma in between those intervals. We're not using union. So with this information, we want to try and sketch the graph of the function f. Now, because the function changes from increasing to decreasing at x equals to -1 and x equals to 1, I want to know what those actual points are on the graph. So basically, I want to find the y values that go with those x values so I can actually plot those points to help me get a better picture of what the graph will look like. So to find f of -1, okay, I'm substituting -1 in for x, so we'll have 1 minus 3, we have 2, so -3 I believe we get, so that's the point, -1 comma -3. And then to find f of 1, that would be -1 plus 3, so 2 minus 1, so 1, and the point 1 comma 1. Okay, so these are actually points that will lie on the graph of f. So let's go ahead and plot those. So -1 comma -3, that doesn't look right, huh? So that would be 1 minus 3, which is -2, minus 1, yeah, it would be -3. It's been a long day. Am I having adding issues? Okay. And then 1, 1 here. Okay, so between -1 and 1, the graph of the function is going to be increasing. Okay, so it's going to kind of have to go up like that. Actually, we can find the y-intercept too. So f of 0 would be -1. So the y-intercept is actually -1. So we know the graph is going to come up and pass through -1. Okay, and then the function's decreasing from -infinity to -1. Well, decreasing means that it's going to have to kind of come up this way. And this is a polynomial, so there shouldn't be any sharp corners. I should probably make this look a little more rounded, smooth, and continuous. And then the graph is also going to be decreasing from 1 to positive infinity. Ugh, I'm having issues here. So it'll come back down like that. So we can see that there would be horizontal tangent lines at x equals to 1 and x equals to -1, and then to the left of x equals to -1, right, we would have negative sloping tangent lines. To between -1 and 1, we would have positive sloping tangent lines, and then from 1 to positive infinity, we would have negative sloping tangent lines again. So you could graph that on your calculator to confirm that the graph would look something like this. All right, this next example here, we want to, again, first find all the values of x where the derivative is equal to 0. So let's do that. F prime is 3x squared. So if we set the derivative equal to 0, easy peasy, x is equal to 0. And we want to determine where the function's increasing and decreasing again. So we'll make our analysis line, but just with 0 on it. So I want to choose a value to the left of 0 and a value to the right. So again, we'll evaluate our derivative at those test values. And we end up with +3 for each of them. So the function is actually going to be increasing to the left and the right of x equals to 0. However, we do know that the slope of the tangent line at x equals to 0 will be 0. So the function is going to kind of level out at x equals to 0 and then start increasing again. So go increasing, 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 then at x equals to 0, level out, and then start increasing again. So I do want to find what f of 0 is. And if we look at this function, this polynomial function, f of x equals x cubed minus 2, you guys know that's x cubed shifted down to units. You know what that looks like. But we're just kind of confirming that the derivative is telling us the same thing that we already know about this graph, about what it looks like. So f of 0 is going to end up being 2. So we know the point 0, 2. Oh, 0, -2. So sorry, -2. Okay, so the graph is increasing to the left of -2, and it's increasing to the right of -2. But it kind of levels out at x equals to 0. So the graph will look something like that. Okay, you guys also know what -1/x looks like. But we're going to follow the same process as before. We want to find the derivative and set it equal to 0 to solve for the values of x where the derivative is equal to 0. To take the derivative of -1/x, let's rewrite. So f prime of x would be equal to x to the -2nd, which is 1/x squared. Now the thing is, when we set the derivative equal 0, there's actually no solution to this equation. There's no x value or no real number that would make this a true statement. So we still want to use our derivative to help us determine where the function's increasing and decreasing. So looking back at the function, we know that the domain of the function f is negative infinity to 0, union 0 to positive infinity. And that's because there is actually a vertical asymptote at x equals to 0. It's where the denominator would be equal to 0, so the function's undefined. And the function can change from increasing to decreasing or decreasing to increasing at a discontinuity, like a vertical asymptote. So for part B, I'm going to actually put 0 on my analysis line, and just remember that that's a vertical asymptote. So putting negative 1 and 1 on the analysis line again, f prime of negative 1 would just be 1. F prime of positive 1 would also be 1. So the function f is increasing to the left and the right of 0. Now, we know there's the vertical asymptote at x equals to 0. It's also helpful for sketching this graph to remember there's a horizontal asymptote at y equals to 0. If you were trying to determine the end behavior, you could think about taking the limit as x approaches positive and negative infinity of the function, and you'd get 0, which means there's a horizontal asymptote at y equals to 0. And you would probably need to do some test points to determine if we didn't already know what negative 1 over x looks like, which you guys do. It's 1 over x, vertical reflection. So let's go ahead and sketch the branches of those. Okay, so this goes along with where, oh, I forgot to write the interval where the function's increasing, decreasing. I forgot to do that for this one too. So going back to this one, looking at this function, there's no discontinuity or anything. The function is actually increasing everywhere, all real numbers, and decreasing nowhere. Okay, remember that pre-calc definition of increasing and decreasing. As x is getting larger, the y values are actually getting larger for every point or every x value on this graph, right? So even though at x equals to 0, there's a horizontal tangent line, if we thought about an x value directly to the left of x equals to 0, like negative 0.00001, it would have a y value that's less than the y value at x equals to 0. Or x directly to the right of x equals to 0, like 0.0001, would have a y value that is slightly greater than the y value at x equals to 0. So it's still increasing. Okay, so here, because the function is not defined at x equals to 0, since there's that vertical asymptote, we say that the function would be increasing from negative infinity to 0, and then also from 0 to positive infinity. And it's decreasing nowhere. So looking at this graph, we can see that to the left of 0, any tangent line that you would draw would have a positive slope, and to the right of 0, any tangent line that you could draw to the curve would also have a positive slope. Okay, so those points where a function changes from increasing to decreasing or decreasing to increasing are called local extrema. So to demonstrate the idea of what a local extrema or what local extrema are, I'm going to sketch a graph. I don't know the equation for. It'll be a polynomial. Okay, so notice that there's horizontal tangent lines at this point, this point, this point, and this point. Now if we zoom in to this first kind of hill in the graph, right, notice that to the left of the horizontal tangent line for this first one, the graph is increasing and then it changes to decreasing. Well, in that neighborhood, if we were to think about an open interval around that point where that first horizontal tangent line is, the y value at that point would be greater than any of the other y values at the point for points on that interval, or for x values on that interval. So we would actually call this a local maximum, or a relative maximum. Local and relative mean the same thing. Different texts will use different terms, and you should be familiar with both. Then if we were to kind of zoom in or go in the neighborhood of this horizontal tangent line, this next one, the y value at that point would be less than or equal to any of the y values on the open interval around it. So we would call that a local minimum. Okay, and up here, local maximum and local min. Now, or the location, I'm sorry, these points are the locations of local maximums and local minimums. The actual local maximum value or a local minimum value is the y value at that point. The x value or the actual ordered pair just describes the location of the local extrema, but the actual value is the y value at that point. Now, none of these are absolute extrema, right? Like neither of these y values are the largest y value of the function, right? The function looks like it's going to, as x goes to positive infinity, the y values will also go to positive infinity. Therefore, there's no actual absolute maximum value. But in the neighborhood of each of those hills on the graph, we have what we call a local maximum, multiple local maximum values. And then same idea with our local minimums. Okay, so local extrema occur at critical values of a function. Well, what are critical values? Oh, here's our definition for local maximum and local minimum written out. So f of c is called a local maximum if there exists some interval a to b that contains c such that f of x is less than or equal to f of c for all the values of x on the open interval from a to b. Basically, if the function evaluated at this value c is greater than or equal to all the other y values on that open interval, then f of c is going to be the local maximum. And then same kind of thought process for local minimum. F of c is a local minimum if there exists some interval from a to b that contains c such that f of x is less than or equal, such that f of x is greater than or equal to f of c for all x on the interval from a to b. We say the local minimum occurs then at x equals c. Here's our theorem of local extrema. So if function f is continuous on an interval from a to b and c is on that interval, and f of c is either a local maximum or a local minimum, then that means that the derivative evaluated at c is either equal to 0 or the derivative does not exist, okay? And that would mean that there's either vertical at the value at x equals to c, there would either be a vertical tangent line, which we'll see in one of these examples, or there would be a sharp corner to the graph. An example of that would be like at x equals to 0 on the graph of absolute value of x. Okay, so critical values of x are the values of c in the domain of f such that f prime of c is equal to 0. F prime of c does not exist. Okay, we just talked about this. Now, c, super important, c has to be in the domain. So when you're looking for critical values of a function, you take the derivative and you're solving for where the derivative would be equal to 0, but also for where the derivative is undefined. However, you need to double check if you find a value, a critical value or potential critical value, say where the function is undefined, the derivative is undefined, you need to make sure that that value is also in the domain of f. If it's not in the domain of f, then it's not a critical value, meaning there cannot be any local extrema at that point. Okay, so just a side note, local extrema occur only at critical values. However, critical value does not guarantee a local extrema. Okay, so we're going to be using the first derivative test to help us locate local extrema. And we've already been doing this, kind of, although we haven't actually identified the local extrema as we've gone. So we're going to find the critical values first. And then create an analysis line like we were doing, and we're going to test to see where there are sign changes in the derivative of the function, right? So where the function goes from increasing to decreasing or decreasing to increasing. When it goes from increasing to decreasing, we know that there is a local maximum at x equals to c, and f of c is that local maximum. Or if the function goes from decreasing to increasing, then f of c is the local minimum, and x equals to c is the location of that local minimum. If there's no sign changes, then f of c is not a local extremum, x is equal to c is not the location of a local extrema. Okay, so looking at this function, we want to first find the critical value, so we need the derivative. Oops. Okay, so we set, this is a polynomial, so the derivative is a polynomial. Polynomials we know are defined for all real numbers. The derivative is not going to be undefined anywhere, so we're just looking for the values of x that will make the derivative equal to 0. Yeah. Okay, so these are our critical values. X equals to 1/3 or x equals to -1. So now we're going to apply the first derivative test, or use the first derivative test. So we'll put our analysis line, put our critical values in order on the analysis line, and we need to pick values to the left and the right. Okay, so f prime of -2 would be, let's see, so that would be -7. Okay, so positive. And f prime of 0 be -1, so negative. And f prime of +1 would be 4. so positive. So the function is going to go from increasing to decreasing to increasing, meaning there will be a local maximum at x equals to -1. And we want to find the y value because we want to find the actual local maximum value. So let's find the y value that goes with that x value by finding f of -1. So f of -1 will be plus -1 plus 0, so 1, 4. Okay, so 4 is our actual local max. It's the actual local maximum value. And the local max occurs at the point -1, 4. All right, so local minimum then at x equals to 1/3, where the graph changes from decreasing to increasing. And we want to find f of 1/3. And to find f of 1/3, do I have my calculator? Of course not. Give me just 1 second. So we are finding 1/3 cubed. (76/27), which is approximately 2.81. So that is our local minimum. Okay, so let's graph those 2 points now. We know the point where the local maximum occurs. So -1, +4. That's -1. Okay, and then 1/3. This is 1/3, 2.81, somewhere in there approximately. Okay, so local max, local min. Now, for this to be a local max, remember it had to go from increasing to decreasing. And for this to be a local minimum, we had to go from decreasing to increasing. So the graph is going to look something like that. We can confirm that by graphing our graphing calculator. Okay, so for your homework, this is where we ended yesterday. For your homework, you have the first part where you're just looking at the graphs and eyeballing and stating where it looks like the graphs are increasing and decreasing, the open intervals on which they're increasing and decreasing. And then for the other problems, you're going to follow the directions, but I also want you to find the local extrema. So use the first derivative test to help you find any local maximum or minimum values and plot those and use them to help you sketch the graphs of the functions.